This is an interesting problem. We've got a configuration of capacitors, and when the switch between points C and D is open, the capacitors have a certain capacitance. When we close that switch, they have a different capacitance. They act a little differently. So the first thing we're going to do is find the voltage between points C and D when the switch is open. Remember, circuits and potentials are kind of like paths on a hiking trail, and the potentials are like the elevations. So it's given that the voltage between A and B is 210 volts. So if we define point B to be 0 volts, let me just draw the top part of this. So if we say the voltage at B is 0, then the voltage at A is 210. And every point on this part of the circuit right here is 210 because that's a conductor, it's an equipotential surface. Then we drop by some amount, right? We go to a lower elevation if we're on a hiking trail, go down some stairs maybe, and we're at a different elevation, we're at a different potential for this whole middle section here, and that's our voltage at D that we're concerned with. Then we drop again going through this capacitor, and this whole section is at 0 volts. So if we could find the voltage across the first capacitor, the 3 microfarad capacitor, we could subtract it from 210, and it would give us the voltage at point D. If we could find the voltage on the 6 microfarad capacitor, we could add it to the voltage at point B, 0, and we would get the voltage at D. It doesn't matter. We could start at point B and add this delta V to what we had, or we can start at the top and subtract this delta V and get the voltage at D. And then we do the same thing for the lower leg and point C. Okay, let's just focus on the top one for now. We know that we have 2 capacitors in series here, and we know the voltage across the whole series. So the charge on the 3 microfarad capacitor has to equal to the charge on the 6 microfarad capacitor, and that has to equal Q total for the series. Let's find the equivalent capacitance. And 1 over C equivalent is 1 over 3 plus 1 over 6. This is all in microfarads. So I got 2 microfarads. And the total charge is going to be the equivalent capacitance times the voltage AB. 2 times 10 to the minus 6. That's my capacitance in farads. 210 volts. And I got 420 microcoulombs. Okay, since Q equals CV, that means that V must be Q over C. And so the voltage drop across my 3 microfarad capacitor, that's this one, I'm interested in the voltage as we go across that capacitor, is the charge on that capacitor divided by its capacitance. 420 microcoulombs over 3 microfarads, 140 volts. So if I'm starting at point A, and this is 210 volts, and I go through that 3 microfarad capacitor, I've dropped by 140 volts, so I'm now at 70 volts. And if I go through, this is a 3 microfarad capacitor. This is a 6 microfarad capacitor. If I drop through my 6 microfarad capacitor, I should be at 0 volts. Why don't we check just to make sure? So delta V across that 6 microfarad capacitor better equal 70 volts. Let's see what we get. It's going to be the Q, the charge on that capacitor, divided by its capacitance. The charge is 420 microfarads, the same as the 3 microfarad capacitor because they're in series. I got 70 volts. It checks out. Now you should stop the video and do the lower leg yourself. You're starting at A, going through a 6 microfarad capacitor, a 3 microfarad capacitor, and back to B, and you need to find the voltage at point C. Do it yourself and then start the video again. Okay, for this part of the circuit, I get the voltage at C is 140 volts. So I've got the voltage at D is 70 and the voltage at C is 140, so the delta between them is 70 volts. Now we're ready to do part B of the problem. Part B calls for closing the switch, and it asks what's the voltage between points C and D with the switch closed. So here's the circuit going between points A and B. This time the switch between points C and D is closed. So what's the potential going to be between those 2 points? It's got to be 0 because they're connected by a conductor. That's an equipotential surface. They have to be at the same potential. What I think I'm going to do now is redraw this circuit so it's a little easier for me to see what's going on instead of leaving it the way it is here. I'm going to redraw it starting at point A. And ending up at point B. There's our 3 microfarad and our 6 microfarad capacitors. So why don't you convince yourself that this is the same circuit? Basically, in our previous circuit, the bottom part of this capacitor was tied to the top of this capacitor at the same potential and also to these capacitors. And if you come here, this one is tied to the exact same places. So these are equivalent circuits. The first thing we want to do is simplify. And so what you'll notice is you've got 2 capacitors here that are in parallel, and you have 2 capacitors here that are in parallel, and the first one is in series with the second set. The first set is in series with the second set. So we're going to simplify this down a little bit. Before I do that, let me go back and number these capacitors so it's a little easier for me to keep track of them. I'm going to call this capacitor C1, and this one C2, and this one C4, and this one C5. I think those are kind of unique numbers. I don't want to get mixed up with my 3 microfarads or anything else. I think that works. So that means that this is C1 and C2 and C4 and C5. Okay, so I'm going to redraw this. I'm going to start at point A, and I'm going to come up with some equivalent capacitor for these two. I'm going to call that C7, and I'm going to come up with some equivalent capacitor for these two. I'm going to call that C8. And what I find is that C7, because these guys are in parallel, I just add them up. This is equal to C1 plus C2. C8 is equal to C4 plus C5, right? C4 plus C5. And so both of those end up being 9 microfarads. Now I have 2 capacitors in series. Let's combine those into one. I'm going to call that C total. And I get 4.5 microfarads. You can do it yourself. So the total charge for these capacitors in series, the total charge is going to be equal to the charge on either one of the individual ones, right? If Q7 and Q8 are in series, Q7 has to equal Q8 has to equal Q total. And then we know that Q7 is Q1 plus Q2. And we know that Q8 is Q4 plus Q5. So we have a nice relationship here between the charges. So let's find Q total. Q equals CV. And we know C total, 4.5 times 10 to the minus 6 farads. We know the voltage across A and B is 210 volts. And so I end up with 9.45 times 10 to the minus 4 coulombs, which is the same as 945 microcoulombs. And I want to find the voltage across capacitor 7. That's the voltage drop across this first set. So that's going to be Q7 over C7, 945 microcoulombs over 9 microfarads, and I get 105 volts. So does that make sense? Let's go back and take a look, make sure things are making sense to us. We know that the voltage between points A and B is 210. And if we have 2 identical capacitors here, then the voltage drop across the first one is going to equal the voltage drop across the second one. If they're different capacitances, then that's not going to be the same voltage. But because we know they're identical capacitances, we have 2 of them in series, they're going to have the same charge, so therefore they have to have the same potential drop. So if AB is 210, then it has to be 105 across each of the individual capacitors. So that number looks right to me. Now let's find the charge on capacitor 1, because we know the voltage on capacitor 1, right? We know the voltage across the series, the 2 in parallel and that's the same as the voltage across 1. It's the same as the voltage across 2. So Q1 is the capacitance of 1 times its voltage difference, and that's C1 times the voltage on 7, right, because they're the same voltage. So I got 3 microfarads times 105 volts, 315 microcoulombs. And for Q2, we can do the same thing. This one is 6 microfarads, same voltage of 105, so we get twice as much, 630 microcoulombs. So let's do a quick check. We've calculated Q1 and Q2, and we know what Q1 and Q2 have to add up to be. They have to add up to be Q7, which is 945. Let's take a quick check. Q1 plus Q2, 315 plus 630 is 945. So that looks like it checks out to me. That's equal to Q7. Okay, so far so good. Okay, I've taken the liberty to draw what the circuits look like when the switch is open and when the switch is closed. Oops. There. Now I've got the switch closed. So when the switch is open and when the switch is closed, we've got the 3 microfarad and the 6 microfarad capacitors, and same in the other case. And so what I would like you to do is click the video off for a second and fill in what the charge is. Q equals what for this 3 microfarad, Q equals what for this 6 microfarad, Q equals what for this 6 microfarad, and for this 3. So fill in all the Q's in both cases, when the switch is open and when the switch is closed. What are all the Q's? Okay, I'm hoping that your answers are 420, microcoulombs, and in this case 315, 630, 630, 315. Those are all microcoulombs. I can't fit it in everywhere, but I'll try to put it in a couple of places. Okay, so what we want to do now, the question is, when we close that switch, how much charge moves through the switch? So what I'm going to do is take a look. I'm just going to sort of draw this a little bit bigger. We've got point A here. Point B here. So if there's 420 microcoulombs on this capacitor, and A is at plus 210 volts, and this is 0 volts, that means this is the positive side and this is the negative side of my capacitor. So this has plus 420 microcoulombs, and this has minus 420 microcoulombs on it. And this is the plus side, and this is the minus side, and this is the plus side, and the minus side, and the plus side, and the minus side. And so what I can do is look and see at point D here, how much charge do I have what's the net charge at point D, and what's the net charge at point C. And what I notice is that the net charge here is 0. And the net charge here, that's point D, at point C, is 0. And now, after I close my switch, let's see what happens. I'm running out of room. I'm going to go down to another page here. So this is the switch open. This is the switch closed. And the first capacitor is 315, so this is plus 315, this is minus 315. The second capacitor is 630, so we've got plus 630 on the left plate and minus 630 microcoulombs on the right plate. And down below it's just the opposite, plus 630 minus 630 plus 315 minus 315 microcoulombs. So I'm going to add up what I have over here, and the charge at D is a positive 315 microcoulombs, and the charge at C is a negative 315 microcoulombs. So if we started out with 0 charge separation between points D and C, and we ended up with 315, then 315 microcoulombs pass through the switch.